Thank you all for coming out. For those who haven't met, my name is Andrew Case. I'm the Director of Research at Volatility. Hopefully you know what Volatility is if you're in this room. On the volatility side, I started back in about 2009, 2010. At that time, it only had Windows XP support, and some other developers were working on adding like Windows 7, but I was very deep in Linux. I spent most of my college life reading the Linux kernel source code. There was a really cool forensics challenge out where they gave you a Linux memory capture, and there was absolutely nothing to analyze it. So going way back then, I've been interested in Linux rootkits and Linux malware since then, and late last year, I saw this report, and I saw it because I have a lot of friends who know I'm very obsessed with Linux malware, so I guess this hit Twitter and LinkedIn, and then I got 20 of the same message very quickly, which this company, which has changed a few times, it was Aon, they got bought by Straws, got bought by someone else, but they wrote a report detailing a piece of Linux malware, which Linux malware in the wild is pretty rare compared to every single day. There's a million reports about Windows malware, and the report, when I say it was short, it is the definition of short. It was literally 3 paragraphs, a 3-minute read, and I was just annoyed by the end because the report said the malware ran on web servers, it stole credit card data, so it was injecting itself into the web server. It said that all of the activity was hidden from the machine, which in the very short report, I inferred that they did disk forensics and found files that weren't showing up during live analysis. They talked about the fact that it had reverse shell capabilities, and that was literally it. Like the depth that I just explained, it was the entire report. And then the other thing they said, which you'll see on the next slide, is there was truly an interesting persistence technique that no one had saw before and wasn't documented anywhere else. So you might know UDEV. It normally works, but when it breaks, then all your hardware breaks and the machine doesn't boot, and it's quite aggravating. But this is not your normal way to persist on Linux. So if you have a setup in your environment to look for bash scripts under initd or service files, things like this, this is very different. What you're seeing highlighted here, the line that says action == add, that is the entire rule to UDEV. And what it's looking for is major number 1, minor number 8. So these are your device identifiers on Linux. I have it highlighted in here in red at the bottom. This is a couple of screenshots glued together from their report. And basically what this is doing, it's a UDEV rule so it can interact with the hardware, and whenever dev random is initialized on the machine, the malware is going to fire, which is a really cool way to persist on a system, because like I said, it's not a service script, it's not an init.d file, it's just UDEV decided to give you a dev random device, and at the very end, where it says run plus equals, that's a sed xp db, so this is why they named the malware sed xp, but it runs that script with the given command line arguments. So I think if I asked people in the room and they answered honestly how many people are monitoring the UDEV rules in their environment, probably a pretty small group, right? But like every talk I give, or most of them, the answer of course is going to be in memory because we're going to find the malware in memory a million different ways. We're finding it from a random UDEV rule. You probably have 5,000 of them on your production system. That's going to be a little rough. So I saw this, I saw the UDEV rules, I saw the fact that it was a really short report and they didn't put a lot of effort into the report, so I wanted to figure out what was going on. Like I said, I was very interested in this. It's pretty rare to see someone writing a Linux report, and I have the question in red, was the report missing any details? The answer is almost certainly yes before I jumped in. They didn't talk about how the process was hidden, how the credit card numbers were scraped, how stuff was hidden from the live machine. So they had the hashes in the report, pulled it off a virus total, and then I went old school. So I will have to apologize to people that get freaked out by GDB. There'll be a screenshot in here of GDB. I was like having so much fun. I put it on LinkedIn. And then it was like the people over like 40 were like, oh, this is awesome. And then the people under 40 were like, why are you still using GDB? Don't you know about the script that does all the work? And who uses that old crap anymore? I'm like, dang, really dated myself with that one. So I apologize ahead of time. But once I got the malware out of memory, which you're going to see has a twist, then I use IDA like normal, and of course we're going to talk about Volatility 3. So just one slide on Volatility 3 for people who haven't heard me talk about it for the last year now. It is a complete rewrite of the framework from the first line of code. So it wasn't just taking Volatility 2, making it run with Python 3, anything like that. It was completely written from scratch. If you think back to 2008, 2007, when volatility was invented. The largest machine you were going to investigate had like 4 gigs of RAM, and a super huge investigation was like 10 machines. That's quite a bit different now. So we had the ability to make it flexible, scalable, and actually really usable in modern investigations. We have a really nice blog post about this. It shows you a lot of the new features, new ways to drive it from the command line. So give that a read if you haven't. But all the volatility screenshots you're going to see are Volatility 3. Also, I'm going to point this out. Hopefully, I have a strong feeling it wasn't anyone in this room, and you probably wouldn't do it. But when we deprecated Volatility 2, we made the GitHub read-only, which means you can't do issues, you can't like interact with it, because the whole point is to archive it because it's no longer an active project. Since then, I've received multiple messages from people like, hey, I can't create an issue for Volatility 2 anymore, and I can't get this to work, which is the whole point of archiving it. Just, let your coworkers know who are maybe less familiar with GitHub. But we're going to see a lot of Volatility 3 today. So the thing that really got me super interested here, some of the Volexity people in the room got messages about this kind of instantly, is the first thing I did is I got the malware off of VirusTotal. And when you download something off of VirusTotal, it's usually pretty accurate, but sometimes it's complicated, right? Because you think you're downloading the exe, but you get a Word doc, or you think you're getting the executable and it's some other component. So I just ran strings to make sure I was at least working with an ELF file. And the first thing that popped out in strings was a reference to init_module. If you're not familiar with this, this is a system call, kind of highlighted here at the bottom, but it lets you load a kernel driver. So we're going into kernel memory, and that file or the kernel module that's going to load does not exist on disk. You simply pass it a buffer in memory through the system call. The kernel loads that module just off the buffer. And so this has a lot of interesting uses legitimately, but obviously it's the first thing rootkits do. So then I'm like, is this company that I previously named, did they miss the fact that a rootkit completely loaded on this machine, or did they just not feel like writing about it in the report? I have a feeling they just missed it based on their YARA rules that looked for the one that runs from the file system, just the tool itself. But now I was really happy because it wasn't just UDEV stuff. Now there is a memory-only rootkit, pretty rare in the wild for Linux, and we're going to get to have some fun. So this is a screenshot from IdaPro in decompiler mode, and obviously I renamed some of the functions that are being called, some of the labels. But another big thing you're going to see over and over again, so I want to talk about it early on in the talk, is if you're used to normal Linux analysis, so you have your syslog and your audit and all these nice things that monitor the system, say you're like fully compliant with a STIG or something like that, so audit should log some of this stuff, you would be wrong, so I just want to get that out of the way early, and the rest of the talk is very valid. So what happens before init module is called? So this is the call where it's going to load the memory-only rootkit. It's going to call a function that essentially wraps pkill. And what pkill does is it takes a string, and that is a substring for the process name. And any process that has that substring in it is going to kill it. Now the numbers 19 and 18 are the signal. So 19 is sig stop, which basically pauses a process that's running. And then you can see right after the rootkit's loaded, 18 is sig continue, which brings the process back to life. So you're like, I have audit enabled, and I'm really crazy and have system calls enabled. So I should see when this rootkit is loading. I can go through my telemetry and see an init module call. Unfortunately for you, what the rootkit does is it kills off any process with syslog or journal in the name. Then it loads the rootkit, and then it brings logging back to life. So your telemetry, like in many ways, has everything but the memory-only malware. So obviously we're going to need to do memory forensics to figure this out. And as usual, volatility is not affected. I like to put that on as many slides as possible. As far as running the malware, it had a pretty simple parser. So if you're going to go, it's on VirusTotal, or if you're here, just send me an email. I can get you the malware. There was a few different modes, but they basically boiled down to L, V, and U. So it was like load, unload, and then verbose, which was loading everything. So it wasn't crazy to reverse the command line. So you're going to run that userland utility. Make sure you at least just have L in the command line. Very simple reversing. But then you get to this. This is where the malware calls init module. I saw Jimmy's face freak out a little bit because I'm sure you've seen the right side this ugly. So this is a call graph in IdaPro. And if you notice the red line pointing to what is a very barely visible white box, that is what fit on my large monitor at once. and I see people who have obviously used IDA not in a good mood. So I was like, what the hell? Like, I'm not doing this for fun just to give a talk. So I started flipping through the strings in decompiler mode, as you might expect. And this is where the rootkit also got interesting, besides the fact that it was memory only. So how Linux works, if you've ever tried to do large-scale memory acquisition on Linux from many years ago where Lime was the only thing out there, you know you had to compile Lime for every single kernel, every single little version, and the reason for that is the data structures changed, the way that APIs are called are changed, so you have to match that version. What this rootkit does is pretty cool. I'm not exactly sure how stable they're going to keep it, but it works to where they find an existing module from the file system that will load for the kernel, and then they have blanks in the rootkit itself, and they just fill them in with that module. So it's almost like all the things you need to pass the check, they just go steal from an already valid driver on disk. So the module layout, the mod info, the versions, all the stuff that the kernel checks in the module loading scheme, and if none of these are right, or if one of these are wrong, the kernel won't load it. So it's pretty cool. Like, it makes it where you have this encrypted buffer inside the userland malware that you run. It decrypts that buffer in memory, and then it just leaves blanks for stuff it's going to steal out of an existing module, and now theoretically it should load on any Linux system. So at this point I knew this was pretty cool. A lot of times you'll see kernel modules or rootkits that don't do this. They're targeting one very specific victim, so they have like one kernel they support. This makes it where, to a certain extent, it should be pretty flexible, much more like a Windows rootkit that could run on all Windows 10, all Windows 11, something like that. Now, the other thing that I thought was hilarious, but as you might suspect had no effect on the machine, is when you compile a kernel module and you have kernel signing on, you get this flag that says you're part of the tree. So like when you do your normal kernel distribution, you have your kernel modules. The rootkit tries to say that it's in the tree as well, which obviously the kernel is like, what is this, and just skips it. It's also GPL, so we have an open source rootkit, and then you can see where it patches in the version magic. So this is also going to make it where it can load on any part of the system. So very generic. The entry thing, I didn't even know what that was, and then I figured out what it is, and the kernel just didn't even pay attention to it, and it realized it was not part of the normal distribution that was distributed. So this is my old school GDB shot that got me yelled at on LinkedIn, but I did it the quickest way possible. We're going to set a breakpoint on init module. You can see that I got it to run, so I just figured out the command line arguments that were needed. It breaks at the beginning of init module, and if you remember from a few pictures ago, what you send to init module to get your module to load is a pointer to the buffer, which is going to be a pointer to that ELF file, and the size. And this makes it trivial to drop it out to disk because GDB has the memory dumping command where you give it an address and an ending address, which is enough to pull the whole rootkit out. So this is really nice. Before that rootkit can even load and manipulate the system and maybe delete part of itself in memory, we can just drop it right out to disk. And then for people who've reversed rootkits out of memory, you know, sometimes IDA Pro can be a little picky with like the expansion and things. This is truly, if this rootkit was going to load from disk, this is what it would look like, which is much nicer to reverse. So at this point, that company did not figure out that a rootkit was there, which was quite interesting. So now we know that there's a rootkit. We've used GDB to extract it out of memory. And now we're going to mix up some more static analysis and memory analysis to figure out what it's actually doing. So the first thing, basically I took the very few high-level things that were listed in the blog post, and I wanted to prove out what they said just to make sure I was on the same track. So they said that the malware renamed itself to kdevtempfs. On, I believe, every Linux distribution, you'll have a kernel thread named that. So on the running machine, it will just look like another kernel thread. What you're seeing here, though, is 2 lines of output. You can see I'm grepping for that name. We have the first one, which here has a parent ID or a parent process ID of 2. So those are your kernel threads. This is the real one. And then you have random process down here named kdevtempfs, which is obviously the rootkit. Also, it's labeling itself as this, what's supposed to look like a kernel thread, and if you look over here, before I ran the malware, I called it the number 1. So it's obviously renamed itself. This would be enough in just Linux memory analysis to figure out that something's off and that that process has been manipulated. So the next thing I want to do is figure out what does this rootkit actually do. As you'll see, we're going to run some volatility plugins and detect it pretty easily, but that's not really enough, right? We want to know what is this rootkit capable of. Now, the first thing This is the first thing I saw in init module. So init module function is basically like main of a kernel driver. And then I saw this stuff in red, particularly the module alloc and the set memory x. Does anyone know what this is? Have to deal with this pain before? So it's pretty miserable when you see a rootkit do this. You're like, okay, this is already painful enough, have unknown malware. Now it's like amped up a bit. Because the idea is when your kernel module loads, you're supposed to allow that to stay in memory. And then you have all these nice volatility plugins that find a kernel module in memory. They can dump it out of memory for you. You can do all this analysis. When you see this getting set up, you know, like you need more coffee, right? Like this is not fun. So what module alloc means is we're going to allocate an area in memory for modules, but not the one the kernel gave us. So we're going to allocate this area inside of the module bounds. We're then going to set memory X on it, which means we're making the entire module space executable. And then what we're going to do with these mem copies, there's one here, but there was a couple in total. We're going to take this kernel module we just loaded, and instead of leaving it where the kernel put it, we're going to go write it somewhere else. So now all the initial places in the kernel that Volatility would rely on to say, hey, here's this module, they don't mean anything anymore because the rootkit's running from a different place. Now, it would have been a lot to get on the slide, but the other thing it does is in every, no matter how the rootkit leaves its initialization function, it returns a negative 32. And the 32 part's not important. The important part is that is a negative number. So very painfully, if your kernel module says that its return value out of the initialization is negative, just any negative number, the kernel sees that as a failed loading. So this rootkit, what it does is it just copies itself somewhere way out in memory. So again, going back to audit D, even if somehow your audit D still ran after that journal process got killed, it would say, hey, init module was called, we put the buffer here, that address would be completely wrong. So you'd have your memory sample, you'd follow that audit D system call, and you would be pointed to a region that was actually zeroed out in memory, which is kind of pointless. So by returning -1, it tells the kernel like, hey, I wasn't able to load, there was some error in initialization. So all those nice data structures, if you've ever run linux.check modules or hidden modules or modules X, all these plugins we have in Volatility to find kernel modules, they're going to find 0 about this rootkit because there is no module in memory according to the kernel. So at this point, this rootkit is doing everything it can to be annoying, and we are like 30 seconds into reversing. Now, you might be wondering if you've done enough Linux work, how it's able to resolve all these symbols. So this was a chance to show off a new volatility feature. So in kernel memory, unless you turn it off, which is very rare, you have a feature called KLSIMS. This is going to hold the runtime address, so the address on the running system, for every symbol in the main kernel itself, as well as any drivers. And so what that allows rootkits to do is also be pretty generic, right? Because if they want to reference a function, they can just say, hey, KLSIMS, look it up by name, and then they're able to figure it out. So just as a quick tip, if you're ever reversing malware of this type on Linux, IDA is going to label calls outside of the thing you're reversing as a jump out. It has the full hard-coded address, like the full runtime address in the kernel of what's being called. In Volatility 2, this was quite annoying. You would have to sit in vol shell and do a bunch of work to figure it out. In Volatility 3, there's a plugin called KLSIMS, which replicates what the kernel does. And then you can see this address here. We're searching it, the chopped version of it down for the address being called, and it tells us right away it's KLSIMS lookup name. So you'll see this quite a lot where you're calling functions outside your module, but with this plugin you can figure out what they are pretty quickly instead of just looking at a bunch of hex digits that aren't helpful. So at this point, we're actually going to start investigating the rootkit. We know it's in memory. We know, I've said it a few times, but this is hopeless on the live machine, right? Probably why other companies that looked at it didn't find anything. So we have a rootkit in memory. The first thing it does is hook the network stack. So remember, the purpose of this malware was listed as stealing credit card data. But then there was 0 information on like how the credit card data was actually stolen. So one of the ways that works is they hook the IP receive function, which is going to be called for all IP packets, and then they're able to manipulate that data. This is part of how they figure out some of the traffic that's flowing through, and it also allows for activating the reverse shell. This is going to be important to remember because certain like kind of magic packet data is enough to get a reverse shell back out to the attackers. And so this is something we can pick up on right away. This is just traditional API hooking. But by hooking this function, everything that flows through the network stack is available to that kernel driver, this rootkit, before any other software can access it or interfere with it. The handler here, I try to minimize the amount of IDA Pro screenshots in most of these talks, but this is where it gets pretty interesting. So if you're ever looking at one of these on your own, this is the function that is actually involved with the hook. And I basically highlighted in red the parts that matter. So SKBs in the Linux kernel are your buffers. So it's going to copy out the first bits of each packet, do some checks on it, and then if they match, two things are going to happen, or one of two things is going to happen if they match. One is you have your reverse shell. So just being able to talk to this web server across the internet is enough to get a root shell sent back to you from the kernel. Obviously, this is a web server processing credit cards, so hopefully it's accessible to the internet, which makes it pretty easy to activate the reverse shell. The other thing is at the bottom, you can see checks for post. This is where it's looking for credit card numbers as well. So you might think, which no one in the room would, of course, I could look at the live system, investigate the memory of the web server, try to do live forensics, and of course you're not going to find anything, right? Because all that manipulation happens in the kernel, which means you have to do memory forensics to find it. So I don't show the disassembly of this because even with the decompiler, it was really gross. But they look for post, they look for get, they look for things that look like credit card numbers, and then they send them back out when they're sent through. But that was really the main reason I wanted, or one of the main reasons I wanted to look at this malware from that Aon report, because it's like, hey, it steals credit card numbers in a stealthy way, and that was it. Never referenced the credit card stealing again. So I wanted to figure out like how that actually happened. Now, the other thing that was interesting, and I will admit I did not know this function existed, so you could probably guess the first thing we did was figure out how to enumerate it. But the rootkit also looks for some instruction pattern. That instruction pattern was not in my kernel. I didn't feel like going and look other kernels for it. But if some instruction pattern is found, then it hooks device add pack, which is going to have the effect of hooking every packet again. So if, from my understanding of the reversing, like I said, my kernel didn't have that pattern, but at that point, I think you would have it where IP receive is hooked, as well as anything that traverses your actual physical network cards. So I guess if the scanner missed it the first time, it's going to get it the second time, and you have very easy access for those reverse shells, as well as very easy access to steal the credit card information. So this is some more volatility work, and don't get bored thinking, oh, this is system call hooks from 2009. It's going to get more interesting in a second. But this is when we teach people how to do Linux memory forensics. You're pulling memory off of Linux systems. You want to find rootkits in the wild. Linux check syscall and two other ones are the first ones to run. If you're familiar with Windows, you have a couple things that would make this not very useful. One is you actually have signed driver enforcement, so you can't just send a buffer in memory and call it a driver and the kernel will load it for you. And then second, you have PatchGuard. So on Linux or on Windows, you can't hook the system call table anymore. PatchGuard will see it and blue screen the machine. Linux, you can do whatever you want. So in this case, we're running check syscall, grepping for unknown, and we see we have 4 indexes, and then we're grepping at the bottom for 5 indexes, sorry. We're grepping for what those actually are. So we want to figure out which functions are hooked on this system. And if you look, it definitely seems like a rootkit. It's everything involved in the file system. So when files are opened, when they're accessed to figure out their metadata, and then when you are enumerating directories. So that's the get dents. And the other thing I wanted to point out before we dive into the system calls more is another sort of interesting thing this rootkit did is if you look at the common YARA rules to find a Linux rootkit, one of the main things they look for are suspicious system call names. So imagine, like on this slide, you would have a YARA rule that said, if sysopen, systat, sysgetdents, all these system calls that a rootkit normally hooks, if 3 or more of them are there, or 5 or more, or 10 or more, I'm saying this because I actually looked at some of the public rules that people use for rootkit analysis. Basically, you're looking for some number, definitely more than 1, of system call names, and then you're going to say, hey, this is probably a rootkit, it's probably hooking the table. What this rootkit did, which I've never seen this before, very interesting way to do it, is all they did is they found the system call table, right? So that's kind of required. So they're going to look up that symbol name. That tells them where the array is in memory. But then instead of directly having the string for all the other system calls they wanted to hook, they just would use sysopen. And then if you look, especially these first couple ones are all right next to each other. They were just pretty hopeful that the system call numbers weren't going to change, and then it was offset based. And I pulled every YARA rule that I know exists and was in the repos for finding Linux rootkits, trying to find system call strings. They all failed because you can't have a YARA rule that looks for one string. You're just going to get too many false positives. So this would actually be an interesting way to ID this particular rootkit, because of all the ones I've ever seen, they normally just have all the strings right there, especially decrypted in memory. So this was pretty cool. I actually thought like strings was broke or my extraction was broke, and I was pretty confused. So then I went and reversed like how it was actually hooking the system call tables, and I saw the math it was doing. So pretty interesting thing that I haven't seen before. This slide and the next slide is going to be a little bit of background, just in case you're not familiar with these. So the stat command is, in this case I'm doing stat just on the driver that I pulled out of memory. It's going to give you a bunch of metadata, the timestamps, the inode number, the size, all this information about the file. And it's kind of obvious that in order for the operating system to give you this information about the file, it has to know the file exists, right? And so by hooking, say, the stat system call, you can make this go away. You can say if a file matches a certain pattern or matches a certain inode, don't let any of the tools see it. This, as I mentioned before, getDense stands for get directory entry. So this is another one of the system calls that was hooked. When you run, say, ls on a folder and you want to get all the files and the subdirectories, this is the system call that is made. You call getDense, it goes through the file system metadata, whatever that might be, and it returns an entry for each file. And so again, you run ls, you see 20 files. That means that code in the kernel and then back out to user land will have 20 of these to give you that specific information. Now this is where the rootkit that otherwise was very interesting got pretty sloppy. So in the top, this is from the Aon report, where they say memory modification for stealth. The malware modifies memory to hide any file containing the string setxp from ls or find, and then in their investigation, it was used to hide web shells and udev and all of this nice stuff. But of course, they didn't have details of how it worked. So when I started my reversing, that was one of the things on my list to figure out, like, okay, Aon says this, how does it actually work? I saw all these strings together, like you see in the screenshot, and I'm like, come on, it can't be this easy, right? Because if you look at the first four, it's PHP, Nginx, HTTPD, Apache. Those are your most common Linux web servers. And then you have setxp, which is the malware name of what they're trying to hide. So before even reversing it further, I'm like, my first thought is they probably want the web server processes to have access to the real data so that they can like store the credit card information and get the payloads and load all that stuff. So if you look at the bottom, I ran the malware with its normal name, the asetxp-b, with the command line arguments that are needed. And then I ran ls from that same directory, and I get no output because the file is hidden. And I'm like, they're not this like lazy, right? Because there's definitely better ways to do this. So I made a copy of the ls binary and named it httpd, which is this guy right here in the strings. And now I run httpd and the file comes back to life. So knowing this trick, you could actually do live forensics to find some of this stuff, but you would have to know it ahead of time. Now, if you're wondering, if you have a lot of, like, haven't seen many Linux rootkits, you can, inside like your kernel driver, your module, you can store the inode numbers of the files you want to hide, because those don't change. You can rename it, like move it to a different directory. The inode won't change unless you move it to like a totally different file system. So this is hilarious. You can imagine there's like a string or something inside the driver that otherwise was pretty cool and did a lot to hide, but this was pretty lazy and basically proved out what I was thinking from strings. Now, the other thing is I will almost certainly never get back to this, but if someone's interested, I can send you some notes and get you where I was in the IDB. So remember that the stat handler says if a file exists. And we're talking about web servers. So when you go to a website, you know, bob.com/index.html, as part of that processing, the web server has to see if the file that you're asking for exists, right? Otherwise, you get the 404 error. So what I noticed, and I did not finish because it was really ugly. I was just doing this for fun, and that did not look fun. So in the stat handler, so reversing from where the stat system call is hooked, and then you can ask IDA Pro to basically draw you like a forward graph of every other function that was called. And at this point, I had like basically every relevant function relabeled to like something that made sense to me. And starting from the stat call, going all the way down to the bottom, I think I'm highlighting the right part, these are the functions involved in the reverse shell. So I am 99% certain that if you made a web request, like say for some reason you couldn't activate it over the network or the packet, I am 99% certain you could request a specially crafted file name to the web server, encode your like where you want your callback to go to, and that would be enough to get the data back out to you. I was very close to finishing, and then it got like the graph you saw before with 5,000 branches. So that's actually pretty cool, right? Because you could have like network monitoring, you could have other data, but you're probably even like your WAF or something, right, isn't going to stop someone from a reasonably named file that just encodes like where you want the data to go back to. So this was pretty cool. If anyone ever looks at this rootkit, you can try to finish that off, but I'm fairly certain that's what it was doing. Now, the other part I mentioned before, where it does the p-kill, it's going to stop, or pause, I guess would be a better word, pause, and then resume those logging processes. The other thing it does is it doesn't want you to figure out that the module is loading in the first place, and it's kind of a race condition, right? Because the kernel, when you load an unsigned module, Linux isn't going to care. It's just going to like produce messages to the kernel debug buffer to say unsigned module loaded and one that wasn't part of the original kernel, right? One that wasn't part of what your distribution gave you when you downloaded the latest kernel package. So it's kind of a race where just pausing that process might not be enough to get that message to prevent that message from being emitted. And this is something, if you follow like any Linux hardening guideline, if you have your audit D and your syslog going centralized, you're going to look for this message here, module verification failed, which means you're loading some sort of module that wasn't part of the main operating system. So this is where the rootkit continued to be interesting. There we go. So it hooked two functions that are relevant. One is do_syslog. You might be able to guess what that function is for. The other one is dev kmessage. So this is if you run dm-esg on the command line, you get that kernel debug buffer. Most distros will replicate that buffer out to a file under like var log, or the newer ones will be in the journal. So it hooks do_syslog, which is what generates syslog files, and then kmessage, which is your kernel debug buffer. And so what it does there, did not mean to move the slide, this button, what? All right, so this one, it calls the real function. So it calls the real kmessage function, gets the entire kernel debug buffer, and then it basically does string manipulation here to say, hey, if you caught the fact that my unsigned, totally malicious rootkit loaded, that can hang out in memory because who looks there, but we are just gonna strip it out of the buffer that we send back to userland. So as always, volatility doesn't fall for such silly tricks. And what we're looking at here is the kmessage plugin. So this is also, there was a version of it in Volatility 2 that was not great, so we're just going to say it's a new plugin for Volatility 3. This recovers the kernel debug buffer, and this is something you can grep for, right? So module verification failed. Also, sort of like if you're making IOCs, things like that, when you load, remember I said before, it has to like craft the kernel module that will actually load on that system. Part of that is the module data structure that it has to fix up and load. Part of that data structure is a name. Now theoretically you could like leave the name blank or call it A or something, but this one, and I did the virus total, whatever it's called, like similarity search to find other versions of it. They were all called Turpin_AVX2. This is pretty close to actually like a real driver. So AVX2 are the Intel instructions for some fast math operations, but every variant of it that I found on VirusTotal had that name. And then obviously in memory, we don't care, right? Like we're not getting hooked or something like that. We are just going directly to the buffer. The other thing, I have it in blue, the other thing I wanted to point out, for Volatility 2 users who haven't seen Volatility 3 yet, or again heard me talk about it, we have the filters now. So even if you were an expert on the Linux command line and you were great at grep and awk and all those things, it was still really annoying to filter Volatility 2's output. Because say you wanted to grep for the number 12, that shows up in every address, all these metadata fields. So Michael Audie, one of the other core developers, he made an awesome feature called filters. So what you're seeing here with the module verification field, if you ran the full plugin, you would see that's in a column called line. So with filters, you can specify the column you want to filter on. You can specify the substring that you want to search on, and it only shows you that output. So no more awk and like trying to figure out the column number that the plugin outputs. This works on Windows and Mac as well, where Windows obviously has fine string, which is like pretty terrible, right? So filters is super powerful. You can also specify it multiple times across columns, and it does a logical OR. So like in the trainings we've done, people actually like clapped at this feature because of how terrible it was. But hey, I was not asking for a clap. I'm just saying other people, without being prompted, decided to clap beforehand. Let me take credit for code I didn't write. But yeah, this feature is awesome, right? Like you do filters, and when you put the exclamation at the end, you can do full regular expressions like Perl compatible regex. So use this if you haven't. It's the last thing I wanted to show with Volatility 3. The other thing I noticed, which it would be an amazing IOC, so this malware goes out of its way to hide from logs, do all this other crazy stuff, load a memory-only rootkit, but then the process that it spawns, which remember, once the rootkit loads, it turns the journaling back on because that would be like really obvious if it's killing journaling off the system. So that's turning, I'm just gonna talk about audit D because that's the most powerful stuff you have on Linux. So at this point, the rootkit loaded in memory, never touched the disk, blah, 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 but now it's gonna create audit D entries where the home directory of the user and the current working directory of the initial commands are proc, which is like this huge red flag. They could have picked temp, they could have picked anywhere else, but they're dropping the malware initially into proc, which was another trivial IOC that, you know, a home directory that really shouldn't be a home directory. But it was one of the few kind of sloppy things the malware did besides the file name based evasion and hiding the files. But another good IOC, like I said, in your audit D logs, look for logins that start in proc for the home user or the user's home, and you'll be able to find it. So in summary, I think I nailed the time pretty well. In summary, this malware was started off with a 3-paragraph report that was like, hey, it hides credit cards, but we didn't figure it out. And so I wanted to deep dive that after, like I said, many friends sent it to me. It was interesting. Anyway, logging is not going to help you here, right? You saw like the main logging facilities won't tell you about the module loading. It won't tell you about an unsigned module loading, anything like that. And just in case you missed it in the beginning with the init module slide, this never exists on the file system. Not a single byte of this exists on the file system. It is packed in encrypted form in that first executable you run. It decrypts in memory, gets sent through init module, then it copies itself somewhere else in kernel memory. So you're not going to find it through disk forensics, but like everything else, you should be doing memory forensics anyway if you actually want to find malware. So that was a talk. If you have any questions, I think I have a few minutes. And thank you for coming out.